Hello, everyone. In continuing with our text sessions, today many of our scientists, our text group members, are not able to be present today. So I'm going to briefly go over some of the most recent nuances or paradigms and progress uh, that's being made. These are ongoing research that I presented. Again, last week I presented the history of physics. There are a good number of viewership in that. So we are progressing very clearly from classical physics to the present state, the current state of physics. But we are not speculating anything. So it's a very clear understanding because there are a lot of confusions and other aspects. Why the quantum mechanics came into being, why general relativity came into being. So these are dissected, so to say, and then understood in a more fundamental manner where you can even, you know, uh, explain, for example, a high school student what's going on. Because I was teaching a course, fundamental course, physics one, that's just covered equation of motion, the Galilean and Newtonian physics, which are quite simple, and I think I mentioned in that history of physics that the main attraction and why classical physics is so useful is that it's in everyday life, and all the parameters are scalar, they're measurable, and they're well defined. Like speed, your length measurement, we have the time, the clock, uh, and then we have distances described and the speed with which we can go traveling and all aspects where if we compute the speed and if we know the distance that we have to travel, which are all measured in either kilometers or miles, things like that, you can exactly calculate how much more time it takes, and that this is very well used. The other aspect is that thermodynamics, which came into being, and we use temperature every day to describe whether it's hot or uh, cold, with rains and things like that. It's all temperature dependent and very well understood meteorology and the climate predictions. But also that we understand it's used in mathematical physical sciences like in chemistry, thermochemistry, all the forces, all the understanding of the reactions is done fundamentally based on the principles of thermodynamics, thermochemistry, and then different kinetic measurements, things like that. These are all part of the classical physics. But the classical physics has a problem, like I mentioned, the ultraviolet spectroscopy, which uh, make it difficult to understand why that is going on. And then Planck came up with the idea of energy quanta, and that is observed in the transition of orbitals. That if you have an orbital where the electron is spinning around a nucleus, and we know that other four experiments that we did a few episodes ago, the history of physics, described how that came into being, and then it changed plum pudding model and things like that. And we know that it's a highly concentrated nucleus, which classically it's meant to consist of protons and neutrons, and then a electron is spinning around. So this aspect of simple geometry, which is kind of very similar to how the astrophysics, the planets going around the stars and the stars going in the galaxies. A simple picture uh, was quite useful, but and it measured a lot of things. But the problem was the energy transitions between the orbitals of the electron itself does not occur continuously. So there is no continuum there. The discontinuum that working with Emery Taylor also about that, and Christopher and Emmanuel, we are all working on aspects. John Hodge is talking about the scalar theory of everything, but they all point to the fact that, and Christian, yes, He said that everything is quantized, and there is nothing like zero, you know, point, zero aspect. Everything is multiplicative, so that it's all quantized, especially the time itself is quantized. The GERD also has advanced his theory. Uh, so we all are coming together, and Emmanuel publishing how the astrophysics, also in the realm of astrophysics, mostly using the metrics, extending the Schwarzschild metrics and understanding the Einstein goals and other Bugdal and other metrics that describes how the quasars or the star systems or stellar objects are. I mean, we have a book on that. But all these publications also point to eventually my publication here that I'm going to briefly talk about. Again, I'm only going to touch upon, and then you can look at you know, the actual uh, the actual publication, which is also in ResearchGate, and it appears, you know, under quantum gravity tensor collapsing scalars and time space wave function operator in physical science and biophysics. So this is an advancement on the original presentation that I had for the Turkey conference in Istanbul uh, last month. And myself, Istoffer, and Emery Taylor presented that, and I was honored to be the session chairman of that. And then we presented that in an earlier live broadcast on YouTube. You mentioned that. And this particular publication, Physical Science and Biophysics, uh, was published, and most of the material that was presented there is being published here. And essentially talks about, like I said, I developed from fundamental IM Arculus theorem and derived everything. So everything can be collapsed back to that aspect, and it's briefly shown here as well. So mainly I'll just highlight a few points here, not going to go into too much detail, and at a later time we can discuss more. People are interested once they go over these references. And there is another paper that is following and is being accepted from Galley proof. That's you know a paper that goes further than that. It's a next level paper uh, that actually proves how these can be. We can calculate Lagrangian and then put the conditions, classical physics, and exactly matches that, and also it proves the equivalence principle, which I mentioned. The two aspects of the quantum mechanics is the correspondence principle, and the general relativity is the equivalence principle. And still now, most of the models, including standard model here of everything, is based on combining the quantum mechanics with the general relativity, which has been quite difficult. And as I say, we solve one problem of ultraviolet catastrophe. We have the other problem, vacuum catastrophe. We are trying to figure out what's going on. Of course, the holy grail of all of these conservation laws, like I always emphasize. But the interesting thing here is that I proved that, you know, in the earlier you know, on the genre of journals, going through the transforms, converted everything to transforms. So we are not assuming anything is constant, because we know even the Hubble constant or Planck constant, everything is not really constant over a period of time. So essentially convert that, we see that it's a black box. The universe is a black box. So we are trying to, get some signals and understand what's going on, but realistically, that's the problem we are facing. That is a black box, and hence, it depends on the perspective or how you view it. Try to understand, but at best, what's the mechanism what's going on inside black box. Ah. Hi, Emery.
Hmm. He's the only one there.
Oh, nice to see you. I didn't see Christopher coming in today. Uh, you know, and then I don't see others because Christopher was traveling. He is with his family, so I don't know whether he returned. So he has not responded yet. But it's very nice to see you. And last week I just gave a presentation of history of physics because that gives without speculation what was happening in the physics. I just present there. So our things comes much later, but what was going on, why the quantum mechanics came to being, that's what I am describing now, and why the general relativity came into being, why the classical physics was not sufficient. Because even now, I think classical physics is the best one that is describing all the things that can measure, like speed or you know distances and time and everything with the clock is measuring that. But there was a problem of like you also presented about the ultraviolet catastrophe. That one of the things that I am going through, and I have not replied completely because I want to go. I think that's a very important uh, literature that you have provided about ultraviolet catastrophe, and the YouTube. I had to go through that to show why you know why the classical physics was not sufficient. And I'm just describing about a discontinuum aspect that we are studying. That Planck came into be, realized that the only way to solve the ultraviolet catastrophe, which means that it shows that infinite temperature is possible, which is not correct. So it's because of the transitions occur does not occur continuously. You know, which means that we have the orbit electron stays there, and the model that we have developed, especially you have originally argued about the how the cycles, there's a separate charging cycle and there's separate translational cycle movement. So because of that, it's a discontinuous propagation, uh, and that means that that's why the even if you supply some radiation or some energy to an orbit, the electron doesn't automatically jump. You need sufficient energy, and this is called the Planck energy quanta. So that's what uh, that solved the problem ultraviolet catastrophe. And like I mentioned in the last episode, that came into created another problem because quantum mechanics and the general it created another problem that called the Viking catastrophe, which gave a wrong answer to the 0 point energy, things like that, vacuum energy. So that's what we are talking about, uh, and and the vacuum so now we are trying to figure out how to combine the two, and all the models, standard model, TF, everything is trying to do that. But like our paper, your paper that we have published, and many of them are joint papers. We show that how these are not uh, really consistent, and also why general relativity has a problem. Falsification aspects show that general relativity has a problem. Quantum mechanics has a problem. So we are developing higher theory of discontinuum aspect, and that's what I talking about. So the quantum gravity that I'm developing, that I'm showing today. I thought and since you're here, maybe go through briefly the publication I have. That's what I want to do. Uh, so that's what I'm trying to do. So the quantum gravity that I presented. Uh, so this is the paper, the recent paper, and there's one more paper coming up, which actually proves that if I calculate from here, these are all from simple Iron-Margulis model. Initially just Helmholtz decomposition of fields of 0 point and micro black hole, and these are developed from there. And I showed that in one of the earlier papers, I showed that how the universe is a black box. So we are trying to figure out what's going on inside. Like Like if you have a clock that's encased in a thing, we want to see the mechanism. There is some mechanism that's creating the time, the clock. So what is that mechanism we try to figure out? That's like a black box. And of course, the black box we use in, Air Force, in the uh, planes and other, and even probably eventually in cars, black box could be there, which shows the information. And the black box here for the transforms, again, I'm not going to go into detail of the math. I think you have to read, people have to read that. But essentially, I could show that the time and how the gravity is not a force, but it is a gradient, and the time is a tensor, like I showed before. And if we use a fourth order tensor and gravity and the time, they come together, and they have this 4 by 4 matrix, which is like a Schwarzschild matrix. So I can compare them, and it shows that, yeah, it conforms to that. So we can prove that from our theory how the metrics come into being without using directly general relativity, although some aspects are implied there, but it's not necessary. The other aspect, important aspect I bring about is that you have why the dark matter come into being is because you have properties. Here I'm showing, I think here, I don't want to go into all minute math, but essentially we can describe in terms of the action. Um, you know, Differential of the action is what time is. Time depends on the action, but mainly I want to see that I have it here somewhere. It shows yeah, we have the coupling of the gravity. That's what I want to show here. I think it's somewhere here. Without going to details. Uh, so the gravity couples, uh, but it doesn't mean it's interacting. That's what I want to show somewhere here. I had it. Show that. Gosh, trying to figure out where that is. Nature of time, sense activated. Okay. Static time, algebraic. Okay. So somewhere here. I know that I had it. Believe I can find it now. Oh yeah, coupling. Yeah. So three criteria for interactive coupling. So okay, that's the gravitation gradient must couple with the time tensor. So it just couples. It's just sensing it. So gravity knows that there is time. Time knows there is gravity, but it doesn't mean it's doing anything to them. So that's maybe what's happening in dark matter or dark energy. But interaction means the time tensor uh, will curl inwards because of the interaction with the gravity, and that changes the fabric. You know, I won't call it. See, I'm changing the term, and for subsequent paper, I will use the word matrix. So there are only two things. There's entity and matrix. So the matrix could be anything. We call it space time or whatever. But the uh, matrix is changed. So is changed by the time aspect, and how the time came into being. That mechanism also is also I have figured out, but I'm not going to go into detail about that. That's a little bit involved. But essentially, the gravity and the time acts together, and it changes the matrix, and that is what creates the space time. Uh, uh, so it can couple without interaction. So that is like dark matter, where there is no curling, the matrix doesn't change. So it's essentially a noisy matrix. That's why we don't see it. The matrix is noisy, superluminar. Uh, and then I don't want to go into all this math right now, but uh, essentially what this umbrella mode, okay. Essentially what that is coming into being is the uh, Mobius strip and things like that. But again, I want to show one more thing here that, yeah, I showed this in the Istanbul conference that you know that actually the signal and noise, they can create a space time, but this is a discontinuum in the sense that they have a definite shape like a Planck length or something. That's the minimum size you need for observer unit. Anything less than that Planck dimensions, they would be part of the noise. So the noise is everywhere. That's a dark matter. I think that the dark matter, dark energy essentially is a noise. But out of the noise, these things are created because there is a distorted field uh, that creates noise. We call it the DEF in our thing. So you have UDE, maybe like that. Maybe the whole noisy, the infinite thing matrix. Whereas the DEF could be discontinuum is created because you can prove any random process will create locally some distortions, and particularly because they could be monopores and things like that. There it could be there. So they create that, and so we have a curling, you have a longitudinal wave, and locally you have a vortex that's created, and that's what's uh, creating the vortex field is what's creating eventually the local gravity effect. So it's an effect. Gravity is an effect. It's a gradient. It's not really a force. And so because of that, I had one more thing. Okay. So essentially, there are only two things. There's quantum form, like I mentioned, and also a vacuum bath. So quantum form is where just like a vacuum, 0 points, that eventually becomes the cosmic microwave background, and then the vacuum bath, which is a local creation of the vortex that creates the gravity effect and everything. That's a vacuum bath. Locally, you have the matrix being created, distorted, and then curls, and then it forms the eventually the matter. So that's a very simple picture that I'm going to expand. So these are mathematically, most of them are mathematically proven. This derivation. So that's essentially this aspect. And then I calculate the Lagrangian. We have to do that eventually. And then I showed that if you apply the classical conditions, they do conform to that and proves the equivalence principle, things like that. So it is consistent. Mathematically, you can prove that. So cosmic microwave background and all that um, comes in being. And also, I say one more thing is that this interaction, you have micro black holes here, 0 points here. When they usually interact, and they start producing the cosmic microwave, and this micro black hole starts to combine together and create what we know as the gravitational waves because of the interaction of the black holes. Uh, uh, you know, they create a gravitational wave. But what we can measure, this is one of the aspects. There are four types of measurements I'm showing. One of them is this time difference. If you know the source is creating a cosmic microwave background, and then later on is creating a gravitational wave. We know for the same source, we can calculate the time difference, and we can calculate from this mathematics what the time difference is, and we can measure that eventually with instrumentation. Then they conform to that. It proves that this theory is correct. The other aspect, interesting aspect, where came the next paper is the Lagrangian I found is that if you have a pendulum that's hanging up there, and then we don't have disturbance, it's isolated in the vacuum in a chamber where there's no wind or something is not affecting it. My prediction is that there is underneath that pendulum, which is just hanging, maybe just staying there. There is this field underneath, right? Distort field, and eventually that will distort the field and it will start moving the pendulum. So pendulums will start oscillating, and how much time it will take, we can calculate eventually. I may have to code with Christopher on that, but someday we can calculate how much time. It may take a long time. So if you keep it, let's say it takes 10 or 20 years for it to move, and if you can keep it still, we will see then suddenly after 20 years it'll start, pendulum starts swinging, and that is the next proof of this aspect of superluminarity. And there is some kind of a vacuum bath, quantum foam, and all underneath that, which because of the equivalence principle, which I proved, that acceleration is negative g. So eventually it will start, the force will start to make it move because there's enough small force available for it to move. So that's the other proof. There are two more proofs uh, I have to so there are four types of experiments we can conduct, and I think one of them will also uh, I will put it in the next paper. Also, discontinuum physics. We could be able to prove that with that eventually. So those are the some of the things that I'm coming up with. That's my recent papers. So yeah, I think I will stop sharing that. So I don't want to go into the mathematical details, but we'll discuss more. So do you have anything, Emery, to present or anything you want to talk about?
Not really.
Okay. Okay. So I saw, we are trying to complete our paper, uh, the 12th paper, and I am running into a little bit of a problem. I thought that Christopher might be here today, but I will try to go over today and trying to code, and then I have coming out with some problem of reproducing our results because I have to debug the program. There is something in the program that I have to redo it because the first one I could create a pretty good, simulation of our the original thing that you gave me, the discontinuum sine wave. But the second one, where the sine waves are, displaced or shifted, that when I put the code, it's not coming up. It's showing all kinds of some errors. So I had to debug that. I was thinking that I could talk to Christopher about that today because he's an IT person. He does a lot of this coding and debugging and all that. So I was trying to discuss with him, but he is not here today. But I will try to do of my own and see whether we can. The main thing is I know the algorithm that shifts the thing, but when I code it, because in order to show the plot, we have to code it. Uh, something is not working out, so it's showing some errors. So that's what I had to fix. So I hope that I can complete that. I want to have a good output like the one I showed you. For this one, I think for publication we need good output, that a code that can be reproduced. So even if you use that code, you should be able to get the same kind of a plot, and that essentially tells what the math is behind. The math is the discrete Fourier thing. That's the math. So if we cannot even do that, you can say the discrete Fourier transform is the main thing, and the Fourier transform is a continuous thing, right? But so if I show that some of the projects that I'm doing that now. Let me see. So these are the codes. Let me try to. try to show some more things we are doing. Okay, so the code. Okay, so the code that this is the code, original code that I'm trying to put. But when I do that, so we have a nice thing that we showed before. That code is working. So it's a discrete Fourier transform, simple by. So essentially, what we are doing here is we have a Fourier, right? A Fourier. The mathematical formula says so essentially f of x is a sine of something. So that's like the sine wave. But then we discrete it by using discrete form. We chop into simple pieces. That's what the discrete form is. And then we code it. When we code it, we get this type of transform. So this is the continuous thing, continuous wave. This is the discrete thing. So that's okay. So it shows the discontinuum thing here. Uh, so that's what we have so far. But I'm trying to see, I have many codes here, but this one you said is no good. I mean, we want a discontinuous thing. So I'm trying to see how we can discrete. So I'm trying to use a code. So this is what you have. You have amplitude, and then you have this break here, the sine wave, and then you have. So when I code it, I get some code, but when I put the code back, it is giving errors. So I'm trying to make it because it's not recognizing there is a break here. So I'm trying to put a larger break and then and then close it here. So I'm doing all this chopping. You have to do chopping. Here it's a more of a chop. Uh, uh, that again I code it, but uh, so the Python code is one of the things that I'm trying to develop here. So that's a situation. So this is, I hope I'm going to work on this and see whether the code I have, but I had to fix something. I had to debug that, whether I can reproduce these things. And if I reproduce, I can then adjust this continuum thing to smaller things. So we need a larger expanded thing to show that, and then we can show this discontinuum here, and then after that the continuum versus the discontinuum. So that's kind of thing I had to redo it, and that's the situation here. So so that's one of the aspects, and then yeah, I think we covered a lot of things. What is the other problem we had? So that's one of, I think that's one of the main math I think that we need, right? Case 2 and 3.
Yeah, case two is where the immaterial spaces at the crest and at the throw, and then the case three is where the breaks are immaterial spaces are at what you would normally call the equilibrium position.
Oh, okay. So I think I have it here somewhere. Let's see. So these are the other things that I got, exotic things out of that. Some how it will look like in a 3D and things like that. I don't know whether you need that right now, but see, these are exotic things that you can get. So this is your original drawing.
Yeah,
Uh,
that's the one for using Einstein's quantized two-dimensional
yeah,
discontinuum geometry line segment.
yeah. And here the white spaces, which is so that when you plot it, you get these exotic things. But then I coded that, I coded that, and that's how I got that one, which seems to be fine. So you get these type of things also. So that's the initial coding, and then I did, that's a simple plotting. Then I did Python. Python gives more detailed aspects. Python that's using even artificial intelligence. So we get all these exotic things when we do more. And this one, I didn't think I show you how we can curl around the discontinuum, create vortex, space time, things like that. So that's the other aspect. And then you have this. We measured this continuum. I'm trying to see the paper you have. I don't think. Let me pull up. Yeah, we have this, right? This is one of the things that we have. So you have one, two, and three. The one is your, yeah, A, B, C, D denote the zero states. So this is your zero state, and
Yeah,
we
that's
calculate. Yeah,
that's case number three is where A, B, C, and D would be the zero states. So
yeah,
that's where the white spaces would be at A, B, C, and D.
okay. So
And
yeah,
that's the one we're
okay.
actually looking to get.
Yeah, that's what I'm trying to code. And the two is where you have the wavelength using trough, the magnetic wave trough, right? And the other one is the electric wave. Yeah, one is the crest of the electric field. Two is the trough of the magnetic field, and the three is the zero state.
Yep, yep.
So that's what we got the first one. Yeah, case one. But the case two and case three magnetic field is. So I don't know whether I have to input something else to get the answers. But I want to get a good coding. So you have these EM, then you have ME, as lambda, and then you have the lambda is the Q2 DDG, EM is CL, and ME is your CL, and then you have the DL in between that. And we know that because of the measurements, because of the significant digits, we cannot, and that calculation should be fine. We cannot really see that measurement. So that's the problem. That's what it's hidden inside that. So it's a hidden problem. I don't know. It's not a hidden variable. It's a hidden measurement problem because of significant digits. It will not show, even if there's a discontinuum, it will not show up in any measurements that we have so far. So that seems to be fine. So you have discontinuum. There could be discontinuum, but we cannot really measure. We measure as a continuum, and that's one of the. I think those things should be okay. You have the wavelength frequency. Okay. So we did for one wavelength. We can, we as an example, and that should be valid for other. I think that should be fine. So if we can, yeah, I have to show the same thing where the trough is changing, and that's where the problem is. So that's one of the last ones that then I can, if I get the code correctly, then I can adjust it to get all the things. So it's kind of a general coding, which would be very useful eventually, because that essentially is the mathematical generality, mathematical formula, or the general discontinuum wave. So then I think that is a mathematical proof of the theory, because the physical proof, the actual physics proof comes much later. There is like I my contact gravity thing. I think eventually we'll talk about the discontinuum, and that sets up some key experiments I don't know how easy or difficult. I'm trying to make it as simple as possible, something that you can measure, which will show. Because we know that because of the significant digit, we cannot really measure that with the normal measurements. So there has to be something like how they measure the black hole, things like that. You have to have something that would measure the discontinuum based on what we are describing. So you should be able
Well,
to.
I'm worried about. See, it's okay to use um, the Planck length as the 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 discontinuum length, but that Planck length, in the way they calculate it, it uses the constant g, which is used by Newton and it's also used by Einstein.
Mhm.
And we're making the claim that, well, Einstein originally made the claim when he said that physics is based upon a discontinuum and not a continuum, which is him saying you're going to have to replace general relativity, is that constant, that g might not be the constant we wind up with.
Mhm.
And you're calculating the Planck length, one of the values you're using is for that g. And if it
Yes.
turns out that it's not really that, then we would have to have a different, it would turn out to be a different length than Planck's length because you would be changing the value of g.
Mhm.
So, so for the
Yeah,
time
that's
being, we're using it, even though we know there's a possibility that its actual size might in fact turn out to be different.
yeah.
But the fact that it's so minute that you really can't measure the darn thing because of that significant figure uh, problem. The but that's really exactly what we're looking for because it provides an explanation for why the discontinuum line has always appeared as though it's a continuum line.
Mhm.
And that's exactly one of the reasons we're the the explanation for why we never knew that it was a discontinuum to begin with. Well, I
Mhm.
provided two explanations. The one is that the length of the DL is so tiny, we just never noticed it, and that's
Yeah.
what you're saying about the significant figures. And the other one is because there's actually five realities. So
Yes.
we've got that one already with the table of realities. It's this other one that with the math that we're unsure of.
Yeah. So one of the things is that what I was saying is that does not my model does not assume any constant, like because of the transformation, and I am purely transforming with the quantum gravity paper I showed you, and hopefully I'm thinking that we can measure the time difference between the cosmic microwave background and gravitational wave for the same source, and that time difference from the time difference we can prove that it's quantized, so that from that quantum time we can calculate the discontinuum length. So that's a huge math. Because I read also Christopher because he's talking about a four-dimensional space and everything, because we have to include the space. So the time and the space come together. Right now it's like 10 dimensions probably or more, like the string theory, but we'll compress it to the Euclidean. I want to compress it to the Euclidean level. I mean, three-dimensional level. Uh, and I have shown some geometry where we can do it. And then I'm working with Christopher, and he also has shown some length measurements, and that from there the if the time that we prove that time is that quantized or discontinuum time, or I call it gauge time. If we can measure that, then we measure the DL, then we can measure DL, and that does not include G or any constants that we know so far. That's a pure measurement. which does not talk about any constants, not even Hubble constant. Even Hubble constant may not be constant. That's what I'm saying. Over a period of time, that also changes. So we cannot use any of those constants. We just purely measure the time and prove that that time is discontinuum time or quantum time. Like Christian also is saying that it should be time should be quantized from his uh, from I-space theory that he has. So if you put together all that, and then with Christopher's space aspect, the hyperdimension, we should be able to calculate. I mean, it's a highly involved math, but I think if we code it correctly, and he has a lot of codes in that, and I also want to code the time thing I have. Uh, I think the calculation. It may take a little bit time, but eventually we should be able to calculate what the DL should be without using any of these. And then we say what that value of the DL, how it compares with the Planck length, will be an interesting thing. And then that will show why we can or we cannot measure. If the DL, for example, is much higher than the Planck length, it probably it is. Because Christian thinks that the time quantization may be like 10 to the power attosecond or something like that, or 10 to the power minus 18 or minus 21 the most. So much higher than the Planck time, the discontinuum time. So if that is the case, then the discontinuum length will be much higher than the Planck length. And then why it appears as a continuum is the big question. That has to do with orbital, like Rutherford's thing, that nucleus, and then we measure the Bohr radius, right? The Bohr radius or the classical radius, and also from the quantum aspect, what the radius of the electron is. Of course, the problem with the quantum mechanics is that electron itself is not a particle, so we don't have a proper radius. It's just a cloud around that, and we see the density of states. So the DL is somewhere hidden in that, cloud. If we think that is a cloud, and then hopefully we can prove that whether it's a cloud, it could be that the electron is spinning around, is vortexing around the nucleus. So much like the aphelion, or like the Earth and the Sun, there is a closer point, perihelion, aphelion type of thing. So it may be coming closer, and then it goes further. So it is spinning around, going around like a vortex, and then you have definite length. Then you have so the DL describes how much close they can come to, but they keep that distance all the time when it comes around. So that may be where the discontinuum aspect may be coming into picture. So that's a very precise description, and and then using this, if we can measure that and show that indeed that's how the electron, and that's why we have the transitions occurring only when you have a specific amount of energy going in, a quanta of energy, then only it will transit because of that. And you connect that with the discontinuum length, I think we have proven essentially, the first level at least, the discontinuum physics. So that is that makes sense, because I wouldn't think it will be easy, but at the same time, I think you have developed the theory, and then if you do the correct math, complete math, which naturally will be involved. I mean, I don't say it is. I don't want to say, just say it's a very simple numerical calculations is going to give us an answer. So we have to develop the whole thing, and that makes sense to me, because I wouldn't think why people, and I know that people are doing too much of math, which were concerning to me. But I think that math, all the math, the TOE is so much of math there. Uh, and so we have, so let me, I have something that briefly I'll show. Again, I'm trying to do the Occam's razor, the simplest measure, simplest explanation is the best explanation. So we don't want to complicate with too much math, but to the level that is necessary. So first we describe the physics, which you have described. Then we use the math to, oh, actually, I should put this one. Let's see. Oh, I think I can show, I don't need this one. I can show this here. Okay. Yeah, yeah. Let me see. Yeah, remove this. Is it? Okay. I think it's okay now, right?
What are we
You
looking
get
at?
it? Yeah. So essentially, this is a simple explanation of what I'm showing here is that how the electric field is very similar to, you have the normal thing, like you have electromagnetic wave here, okay, that splits into electric field and magnetic fields. So we use outer product in a product, the bra and the ket aspect just to describe the fields. So electric field occurs like that, and this is what we see, for example, in the noise, or what we call the DEF or UDE. They split up; they don't occur together. So that's why we cannot measure that. But the distorted field, when they come together, they create electromagnetic wave, which is what we call the light or the photons. So, and this electric field, what I'm showing is, I showed this one, the quantum gravity. The time and gravity acts together to produce this vector. I don't know whether you can see that. Try to zoom in. So this is, I know. Christopher has a way to zoom in, but I don't have that here. But I think you can be able to see. This is what I show in quantum gravity, my paper, that these two occur separately. The time as a tensor occurs separately, and gravity as a gradient, which is not a force. So it occurs separately, and they come together. They couple, but they couple and they create this this matrix I showed you, the 4 by 4 matrix, for example. Uh, and they come together, so they can go back and forth. I can also have this matrix split up into the time tensor and also gravity gradient tensor. So they can split up, like very similar to how the photons can split up into electric field and magnetic field separately. They can split up that. So the electric field, if we compare that, and that's the proof I'm trying to come, maybe like this time aspect, magnetic field may be the gravity aspect. So the gravity that we see a gradient is actually a magnetic thing hidden inside that. So it could be like a monopole or something that then becomes the gravity effect attraction. So in one of the papers I show that. So which means that uh, the gravity gradient, we can measure the gravity in terms of the, like I say, vacuum bath, the gravitational wave, and this aspect of the electric field measures as CMBR. So I can measure these in terms of the cosmic microwave background. This is a gravitational wave. Uh, so then we can connect all these stuff together. Like I say, the measurement of the quantized time or discontinuum time, because if it's the same source, what I'm saying is that if it's the same source, then we have the CMBR. Okay, this becomes the CMBR, and this becomes the GW, which is the gravitational wave. So if we can measure the time difference between these two, and if we prove that it's quantized by some very clever experiments, then that will be our primary uh, physics, experimental physics, which then proves the discontinuum aspect. That's what I'm trying to come up with. But I'm developing all the math, eventually connect with Christopher's math, and hopefully maybe even Christian's I space. Then we can connect to a discontinuum physics to calculate the DL from the time difference, and then calculate the DL. That will be a complete math. And then we do some predictions of what the time should be, and then we measure the time, and if it is coincides and better than anything that we know so far, including theory of everything, then our theory is much more robust and maybe the most fundamental theory, but there's a few steps to go. I don't know how long it will take to calculate, but I have an idea of what we should be doing. I mean, we didn't have so far an idea of how we should go about figuring that out correctly, um, in a rigorous manner. But we are then rigorously we calculate the DL. Then we say, okay, it's either very close to Planck length or much higher. But again, the significant digits and other aspects, why we cannot measure that in a mesoscopic level is what we can then explain. Uh, the waves, the discontinuum aspect of the wave, although there is some physical explanation we have, like we don't see a continuous radiation coming out. We see that the radiation itself is a discontinuum. Uh, and the very fact, there's another simple explanation, is that the very simple fact that the matter occurs is a discontinuum. You can say intrinsically it is discontinuum, because the matter, when it exists, it has a finite size and dimensions. Uh, but if it doesn't exist, then it's like noise. It's a continuum. So the very fact the matter or particles exist intrinsically means it's discontinuum. It's continuum from the matrix. That's what I think. One of the things I want to and developing is the idea of matrix and the entity. So yeah, if I can, I think in one of the other papers I'm right. I'm just it's in the writing stage now, but I think I want to develop a robust math for all this, which will take a little bit time, but I think that will be useful. Yeah, the four experiments I'm talking about briefly here, although I need to rewrite this to understand that. Like I said, that CMBR, the time lag from the unit source, the same source, time lag between the CMBR and the gravitational wave. That's the one experiment. That experiment I talked to you about the pendulum, and there is some noisy thing that can actually move the pendulum. Like I say, calculate the time that it takes, and then we can prove that indeed, even if we keep the pendulum static, after a long time they'll start swinging. So that's another proof. Then we have the third proof is evaluating the CL, like I mentioned, the continuum length and our discontinuum length. That's the fourth one, uh, measurement from the rank 6 and things, which I described briefly right now. So these are some of the things. And One more thing I have. These are ongoing things. I'm just developing that eventually. I think there is reasonable amount of math and confidence that we can develop. Uh, and one more thing is I can write it out separately. But I'm trying to see what I have. It's about the entity and the matrix. Basically, that's what I come into. Um, that's a very, very detailed thing, very interesting thing, because that explains most of it. I think it'll explain, once the math is developed, it'll explain why things the way they are. Yeah, it's written. I have to rewrite this one, but essentially we have the. I might write it here. It's here. There are only two things: entity and matrix, and they contain space, time, sense, energy, particles, and like quarks, matter, quarks, holes, environment. Sorry, when I write this one, it's hopefully you can read this. Okay, so this is what basically I don't know that you can see that. So there is only two things: entity and matrix. So if you use a simple 2 by 2 matrix, you have entity and then you have matrix. Then we have no entity, matrix, nothing. So we don't have both. This is like vacuum. It's neither entity nor matrix. Then you have both entity and matrix. And that's what we are. We are both entity and matrix, both, like mesoscopic life. So entity, what is entity means? Entity can be any particle. I believe that the entity comes in the matrix. So if you have a matrix here, which part is the brain? So this is a matrix, and it has a brain inside, BRANE. So it's matrix brain theory. This is very close to M theory. So you have some matrix which is like a noise here, but inside that matrix we have holes, and we have particles. So the holes and the particles come together, much like a semiconductor theory. The hot they come together, and this is could be what I was showing about the quantum form or the 0 point field or our DEF, and then we have this micro black hole. So they go around and they create eventually locally distorted some big matter or particle, and inside that it has locally it has what we call the space-time energy matter. So you have energy matter coming together there. So this is localized, and much like we saw in our in my materials, that this happens, a nucleation happens here. So you have it, initially it will be unstable, but with the proper in proper time, they all come together and they create a stable thing. And this is the starting thing that creates the universe. We call it black hole theory and everything, but this is like a matrix. So it's always there is a matrix, and these things are going on all the time. These things are going on all the time, but it produces a discontinuum here in the matrix because of the dynamics. I call it hot PDP mechanism that creates the particles, and that creates the universe. So in terms of the singularity, this may be seen as singularity, but realistically it's just a discontinuum. Um, so that's the idea. So there are only two things. So entity and matrix. Entity is what is not matrix is entity, uh, but entity is part of the matrix. So this is the whole idea. But we have to have the two different things, like the reality. So then you can connect the reality, how this reality comes to being, how the vacuum does not exist by itself. It's just a dynamic existence. That because of this interaction, the vacuum. So what happens is interaction creates a vacuum around this. This is how the vacuum is created. And this vacuum then explains very similar. So this essentially become, the atomic level, this essentially becomes like a nucleus. This is a vacuum around that, and then you have the electron outside of that. So very similar to our picture of nucleus. You can see that is consistent with that, but then you have the vacuum, and then you have the electron here. So it's very similar. So there's a space between that, and this space, like mentioned, is spiraling around like a vortex. So you have the nucleus here. The spiraling around is the electron, but this is not a continuum. So this could be, like you said, the break here. So they don't. So that's one we have to prove. So they go around, they jump from here to here. The electron jumps. So it stays here until it gets charged, then it jumps to the next level and moves like that. And then it creates, because of the balance of forces, it maintains certain finite length. Finally, we call it the electron radius. So electron radius creates. So that's kind of a picture that comes in. Doesn't doesn't assume the quantum mechanical aspect, but it says that it's vortexing around. And people are, one of the things that Bohr, the quantum mechanics say is that the electron comes around, it will radiate, it lose energy and it will fall down, fall into the nucleus. So that's the theory. He said that he came up with the idea of orbitals, that it doesn't do that because it has a finite size. So the quantum mechanics says it has the wave. So it forms certain wave which prevents it from falling down. So this is what Bohr was saying, the Bohr aspect. But what we are saying is that it's a discontinuum. The wave itself is vortexing. It may be vortexing, but it's discontinuum. So there is no need for it to fall down. So that's a slight difference. This is a continuous wave. So you have DL, your DL here, your CL here, and they maintain that space Because of that, the electron does not fall down into the nucleus. So that's basically a fundamental conceptual difference that we are trying to develop. Okay, so I think that's what I have kind of. I'm briefly explaining. I'm not given all the math or anything, but that's kind of an overall picture, of for of what I think, what we are doing, and that you may comment on that, or you may add something to that. Okay, Mary.
Well, I sent you an email just before I got
Ah,
on
I didn't see
here.
that.
I
Yeah, I didn't.
figured I figured out how discontinuum physics can account for what they call spin angular momentum.
Oh, okay. I had to read that. Yeah.
I was well.
I can pull up that. Let
I
me see. I can
frequently
pull.
watch different. Yeah. All right. I
Let me try
frequently
to pull
watch
up that.
different videos about different things.
Hmm. So let me see. I can probably pull up that. Let me see whether I can pull up that, and we can discuss that right now. Yeah, yeah. Okay. So let me do this. And I have to present. I think I have. Now you can see that, right?
Yeah, I can see it.
I'll just magnify it so you can see more clearly. So, oh, I had. Okay, so you have this. Okay. So you're saying the sixth reason discontinuity is more fundamental than quantum mechanics. Spin is a form of angular momentum. A body moves along a curved path, such as a satellite revolving a parent body in orbit. There's angular momentum when a body such as satellite rotates about its axis. There's angular momentum. The DCP atomic model, which makes use of Bohr's model, within an atom, uses Newton's mathematical point, the tangential reference frame, electronic times that are not instantaneous. Property of speed is the requirement that a complete oscillation must occur for the emission of electromagnetic radiation. It's continuity of the absorption and emission process, which are all the previous papers. Yeah, it's results from electron transition must be considered as the electromagnetic radiation discontinuity. TRS. The TRS is our okay, yeah, tangential reference system, perpendicular by acting direction the electron travel. For the TRS, the electron is point-like motion. So each point of its path only exists when the center of the electron is at that point. So you are not saying that the electron is a cloud, right? In this case, it's just the because of the realities. Is it because of the realities that it comes into being? The electron.
Well, in the in the previous papers about the DCP um, model of the atom, which of course uses Bohr's, we claim that the we don't describe what the electron is,
Uh-huh.
and we claim that it's a point, a mathematical point on the y-axis, which is the tangent reference system. The other end of the y-axis is the mathematical point at the center of the nucleus. So we never claim if it's, like a marble or if it's a cloud or anything. We don't make any claim about that at all. We just say that whatever its center is, it's on one end of the y-axis.
Oh.
So we don't make any claim as to any shape or anything like that. And the point that we're using is Newton's mathematical point. It's not a physical thing. It's not a non-physical thing. It's just a mathematical thing. And the because we're using Bohr's model of the atom, he has stable, or what he calls allowed stable orbits that are at allowed energy levels. And for DCP, the path that the electron would travel, you can show a path, like, for example, the path of uniform curvature motion is just like a circle around the parent body. Well, that circle is not actually realistic because every single point of the circle that's of the path around the parent body, all of those points only exist when the mathematical point of the electron is at one of those points. None of the other points exist. Only the one that it's at is the one that exists. And you can say that for every single point of the path that it travels. So it's actually it's not in uniform curvature motion, it's actually in point-like motion is what it's in. So you only have to actually refer to one point. That's it, just one. And for that one point, the center of the electron is that mathematical point that's at one end of the y-axis. And for something that has angular momentum, for example, being in one of Bohr's stable orbits, it would have an angular momentum. But for point-like motion, that angular momentum would be just something that's inherent to the point, and there's nothing that actually is revolving or spinning because you're dealing with point-like motion. You're not dealing with normal motion.
So you are saying that it's an abstract and it's jumping. It's jumping one point to another. Is it like that? It's not continuum. It's just one point and the point then jumps. The mathematical point supposedly it's an abstract
No,
concept.
there's no jump. I know you get from one point to another point, but see, you're using a continuum there, and we know there is no continuum.
Yeah.
So there would actually be a small space, but we don't have to consider it to be a jump. The point-like motion is there's always just that point. There's never any other points. Because the only point of concern is at the end of the y-axis where the mathematical point of the electron is. And it's always just one point at a time. It never is. See, that's what I was trying to explain about on the table of realities for a subatomic particle, which the electron is. the reality that's applicable to it is no continuum reality, which is non-physical reality. So there's no continuum,
Mm.
and the the time doesn't elapse, and the 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 space, there is no actual size to it, which is convenient because we're using Newton's mathematical point. But the time doesn't elapse. It's always just it's just that point in time. It's never any other point in time. So all of the points, and see, I was describing it as Bohr's stable orbit. Well, that orbit's being described by uh, a continuum, a continuity. It's a continuous line, but we know that doesn't exist. And for the subatomic particle, which the electron is, there's always just the point in time, just that one point in time. So essentially, what you have in order to show that it's moving, and we're saying that it's not moving because it's point-like motion. But if we were using Bohr's version of the stable orbit, what you would really have is you would just have, like you have for each point of that continuity, there would be like a sheet of paper, and there would be a point on the sheet of paper. And then if you had how they make a cartoon? They draw an animated cartoon, they
Yeah, yeah,
draw a little bit, then they have another page, they draw a little bit, and another page, and then when you flip the
yeah.
pages, it looks like it's moving. Well, it would be similar
Oh,
to
yeah,
that.
yeah.
It would be similar to that. You would have all the points of that orbit, and then you would, on different sheets of paper, and then you would flip the sheets of paper, and it would look like the point moves around in a circle. But it's
You
always just the point. It's never anything other than, see, that's what I mean by point-like motion. You got to think of it as like that animated cartoon where, each sheet of paper has the point at the mathematical point of the electron at a different location. And then when you flip the papers to, it simulates that the point moves around in that
Mm.
circular orbit. But we always only have just that one point on one sheet of paper. That's what I mean by point-like motion. And so when you consider just that sheet of one point of where the electron, the mathematical point of the electron is actually at, well, there's no other points. So there's no motion around the nucleus. So there would be no angular momentum in the way that you normally think about it. But momentum has to be conserved. So for each one of those sheets of paper, that momentum has to be conserved when it's just that point. So that point has an intrinsic or inherent angular momentum, but it's not represented. And that allows you to then use your quantum mechanics where it has there's two states. There's either an up one or a down one. But the electron, even in quantum mechanics, it's not actually spinning. There's no motion that's causing the angular momentum. And that's what I was going to say is I was watching videos about the angular momentum in quantum mechanics. And I was listening to people who are particle physicists, not just somebody from the general public. And they were saying, well, they don't know why the electron has this angular momentum, even when it's just all by itself. Well, the reason it has that is because of the point-like motion and the angular momentum. Remember, we're using Bohr's model of the atom. The angular momentum that it would have if it were actually traveling like Bohr was claiming has to be conserved. So for the point-like motion, it's just something that's inherent or intrinsic. It's an essential part of the mathematical point itself. There's There's nothing that's actually spinning. But for that point-like motion, that angular momentum has to be conserved. And so that explains why you have it in the first place. You use DCP to explain why you have it in the first place. And the reason is because you're using the tangent reference system, you're using point-like motion, and you're using the property of spin instantaneity and the fact that those three things together form a discontinuity, which is conserved as the electromagnetic discontinuity. But it also has something else in it. It has that angular momentum, which of course wouldn't apply to the photon, but it would apply to the electron. And when emission occurs, part of the discontinuity flies off with the photon, but the rest stays there with the atom. And it would be in that point-like motion that that momentum is, well, essentially trapped there with the electron. And that explains why the electron has it.
Yeah. So it could be okay. One of them is you are saying it's an abstract. That point itself is an abstract. Doesn't really
Yeah,
exist a mathematical point.
when we in those previous papers, we never actually said that the electron had any shape at all. It was just an abstract point, Newton's mathematical point on the y-axis. That's all we said. We never said that it was shaped like a marble or that it was an electron cloud or anything. It was just an abstract mathematical point. That's all that it was.
Okay. Is it possible? I mean, this is the other aspect I was thinking about. We can write here. So suppose we have something very simple. So we have like thing. I mean, the aspect of tensor comes here. So we are looking here. This is our eye. Let's say we're looking here. We see only these points. See, this is the y-axis, the x-axis, something like that. So we see only these points. We don't see these when it pops out. So this aspect, what I'm saying is, could be like a tensor. The tensor we cannot see. This is now scalar. So when it becomes scalar, we actually see the point. So all other points exist as a tensor, like time tensor or something like that. Even gravity, all those things. This is we cannot see this. Not observable, non-observable. And this is observable. The scalar exists. So the scalar does not exist continuously. It is continuous when we see it. This is one of the problem, the double slit experiment. That one of the things I think the next one I describe a little more about double slit. But a double slit says that if you see it versus you don't see it, there's a difference. When we see it, it exists. Like even the quantum mechanics says, the wave function collapses and we see it. If it doesn't, it doesn't exist. So these kinds of things. But what we are saying is you are saying is intrinsic. It's nothing like we are seeing it or we are observing it, but mathematically, this exists some point as scalar, but then it doesn't exist because my explanation would be it exists as a tensor, which means we cannot see it. And then at later time, there's no time. So in the tensor, we cannot define time. There is no scalar time. There is no clock because we describe in terms of the clock. The clock exists only here. There is no clock here. The clock that we see, scalar, clock or arithmetic clock does not exist here. So this exists. So we see the clock here. So this is so with clock. So the clock is, oh, I don't know, let me put that. I'm on this one, so I have to put this on. Yeah, I was writing that. I think you cannot see that. Let me see. Okay, I don't know whether is it. You can see this now. I'm showing here. Oops. I don't know how well you can see what I'm showing. What
Well,
I
all I can see is the paper. I can't the email that I sent you. I can't see the paper you're drawing on. Oh, I see it down in the corner.
Yeah, yeah. Is it readable?
Yeah, but it's awfully small.
Yeah, I can put it back up there for now, and then I will put that back again.
Well, see, another thing that I wanted to tell you is about the Bohr orbit,
Uh-huh.
the the path. See, it would be represented as like a continuum, and
Uh-huh.
between any 2 points, there's an infinite number of points. But we would be using a discontinuum, so there's not an infinite number of points. See, that discontinuum winds up making that orbit a finite number of points. There's no continuum involved in it.
Okay. So what I'm saying here is that we have this. We are looking at it, from here, from the y-axis. We're looking. So we see only these points because there is no existence here. It's just a tensor. Tensor means there's no real existence. Tensor essentially means. So it exists as a mathematical, even as a mathematical point only here. Because unless it becomes scalar, even mathematical point doesn't exist. So a scalar, and what I'm saying is that that's what our clock is measuring. So the clock cannot measure this one. Clock. The clock measures only these. So they will occur discontinuously like that. So this is suddenly the mathematical point exists here, here, here. So this is your discontinuum aspect that's coming in. And in this tensor form, like I said, a time tensor, there's nothing. There's no interaction between, only when it interacts, like I said, the time interacts with the gravity, only when it interacts, is couples, it's not enough. It interacts, then that comes into being. Then the scalar thing comes into being. So here there is no interaction. Just like in the noise level, there's a UD, whatever, I say it's a noisy condensate, but I think what you describe is UDE only exists here, but the DEF starts existing here. Will that make sense?
I'm thinking it does. Yes.
Okay. Because a clock, cannot measure these things. So which means that text is here, then suddenly we see it later on there, that we see there.
And
So
that's
it's like,
the only thing the clock is measuring.
yeah,
It's not measuring anything between those.
no, there's nothing.
Yeah, I see. Yeah.
So, I mean, my tensor also, is consistent with that. The concept of tensor is consistent because this scalar is the arithmetic, or what we say, this is the arithmetic clock. You know. arithmetically or as numbers we see it. These are algebraic, but the algebraic thing does not have any real existence. So in terms of existence, only these are existing. Real, in terms of even the mathematical point, we see it in one other realities we see as existing, physical reality, whatever, and that exists only because of the clock now suddenly says that oh it exists. So it's very different from what I was saying is different from what quantum mechanics says or about the double slit experiment, which says that only when you see it, it exists. If you don't see it, it doesn't exist. Because of wave function collapse. But what we are saying is that it's intrinsic. It's nothing to do with whether we are observing or not. It's just intrinsic that they exist only here because they become scalar only here. Otherwise, it's a tensor, and the clock measures only the scalar aspect, so they will occur as discontinuum points. So that is what the overall thing is. That might make it consistent, uh, more consistent in terms of conceptuality. Of course, like I said, the actual measurement, actual calculation, the mathematics of it is more involved, and then we have to combine with all those people, Christopher, Christian, all of us, all four of us, and your and then mine, tensor, your discontinuum physics. All this had to be combined together to figure out what this distance is. Uh, we measure, we can actually calculate the measure, and hopefully someday we can actually measure it and then show that indeed that's the case. Uh, so then it explains the problems of relativity and quantum mechanics, why they cannot come together, because what general relativity is saying is that it, you know does it explain it's a continuum here, it says here. This is what Einstein also was saying, that hidden variables or whatever you call it, they exist but they are continuum here, whereas quantum mechanics says that's not the case. They exist as a cloud, and they exist only because when we see the wave function collapses to these points. So that's a big difference between the two. Whereas we are saying there's nothing to do with whether we observe or not, but they exist only like that, even as abstract points, because they become scalar only at that time. So it's just, and then that's only time the clock can measure the time itself, and the clock measures the time, and then that interprets as the space. Then we translate to space, then that then says what the spatial difference is. So we explain the discontinuum or the quantum Q2DDE of Einstein is that he talks about, Einstein also talks about 2 points in one of his things, uh, referential aspect, the 2 points, how they exist. But I think he assumes that this is continuum, and we can actually, and you can measure it, but actually it depends on the perspective. Because if you look at here, if you look at some other way, if you look at this way, suppose I have I here, if I'm looking here, then I see differently. If I see in another dimension, I can see this wave coming out. But what we are saying is that that's not the case. It doesn't exist in a real, in the physical reality even. It's tensor, which is it's totally different, which is hidden in the, yeah, that's the thing. Where is it hidden? It's hidden in the superluminar noisy condensate, or UDE, where everything is all together. There is no distinction. The distinction comes because the reality changes. So here suddenly the physical reality comes, and you're saying that it depends on the your rank, and this thing comes from the TOR, table of reality. You have the quantum here, the astrophysics here, or whatever, and you are somewhere here. You are mesoscopic. So this reality. So it depends on what reality we are talking about, right? So the quantum
Yeah, it depends
reality.
on the reality that you're using.
Yeah. So here you have a different reality. You have a different reality here. You have a different reality. So here, these things occur mesoscopically, or whatever we call it. Um, but the quantum level, if we go beyond Planck level, it exists only as a tensor. We don't see as existence. What happens as astrophysical reality? Similar thing happens there. So yeah, that's something I think we should be able to. These concepts will help us. But we have to tie them together somehow. But I think that seems to be it's a explainable, and also eventually measurable thing. But we have to develop the math, uh, because I have the time aspect. Christopher has the space aspect. Then probably Christian I space. Then our discontinuum thing, that if I can solve that coding problem, then we can see that you know this the discontinuum exists, but we cannot measure because of the significant digit. But we can measure something else. The significant digit will prevent us measuring in terms of the length dimension. But I think we should be able to measure in terms of the time aspect, the discontinuum time aspect. And Christian also is pointing to that. And that may be measurable because we can now measure attosecond, which is, I think, it's 10 to the power minus 18, if I think. But we have to go a little bit more. We have 10 to the minus 20 or minus 21 second. Then we'll start seeing the discontinuum. I think that's what Christian is saying. I think that may be important because if indeed we see but that's what the time is. The time is not a continuum. Hence, if we calculate back, the space is not a continuum. The real space or whatever the observable universe or the matter space, the particle is not a continuum. Uh, so we are somewhere then higher than the quantum mechanics or the astrophysics so far, or general relativity, so to say, uh, because so we are looking here general relativity GR here. We have quantum mechanics QM. Let's say. Then we are looking here. We are looking here. This is our DCP here, and then it's looking these two. So the DCP then will explain both GR and the QMS. If we can combine the math, we should be able to figure out uh, how they came to being, and specific conditions we apply. If we apply specific condition, that becomes GR DCP. Specific condition, mathematical condition we apply, we should be able to get QM, the quantum mechanics. That's the higher theory. Then the other aspect I'm saying is that how does the sheet come into being? You're saying that you have a point here, another sheet, you have another point, let's say, and we move it. I mean, that's how movies were created. And I agree with you about the cartoon because initially people used to draw something and the next drawing may be slightly different like that. And then
Yeah,
when you move it, you get the moving the movie, the actual movie. And we know
right.
that the time difference like 1/16th of a minute or something like that. I think the movement you had to be synchronized to that level. That's how they started getting moving pictures. So if you have different sheets, each should be like a brain. So brain sheet, like a brain sheet. So then we are talking about matrix brain sheets. So then I have somewhere, I don't know, I don't want to go into details here, but how these brains can exist, because they could have positive, negative, like a static thing, positive, negative. So they keep the distance because of that. But they cannot come any closer. So they exist as separate sheet. I think I have described that, and they may bend because of that. Um, so these are brain. So the brain is, these things exist. So in this brain, the scalar exists here, and then the scalar exists here, and then when
And
you come,
the the discontinuum length would be separating the sheets, is
yeah, it should
because
be,
there is no continuum, so the DL would be separating the sheets.
yeah,
So there's always point like motion. There's not there's not a continuous motion. It's always point like,
yeah. So
with the point being on each of those sheets,
mhm.
and the sheets separated by the DL.
Yeah, they also call it Riemann. I call it a Planck sheet sometimes, Riemann Planck type of sheets. But the Planck is questioned because we don't know whether the Planck, DL may not be Planck. So it may be more like a Riemann geometry. So Riemann says they call it a Riemann sheets. Uh, they are separated by certain distance. We call it DL. We don't know
Right.
exactly what that is yet.
Yeah, we don't know what it is yet. Well, we do know it's extremely tiny, but
Yeah,
that's all
yeah,
we know.
yeah. It is much much less than Bohr radius probably. It may be somewhere between, DL maybe. My feeling is that DL may be less than electron radius, and but is greater than Planck length. So this could be the situation. Could be even much greater than Planck length. Could be much greater than Planck length. Maybe even much less than Planck. Somewhere in between. So that could
I
be the
know
problem.
we don't know exactly the size, but you can see what I'm saying is
Yeah.
for Bohr's in the model of the atom that we've got going, we're
Uh-huh.
using Bohr's circular orbit,
Uh-huh.
and that circular orbit is based upon a continuum, which we know doesn't exist. So the
Uh-huh.
points would have to be separated by the DL, which reduces it from a continuum to a discontinuum. So there's not an infinite number of points. And
Uh-huh.
since it's a circular orbit and it's point like motion, you only have to consider one point. That's it. And
Yeah.
the angular momentum that would be associated with the electron moving in one of Bohr's orbits, now it becomes just something that's inherent to that point because it's point like motion. There is no circular orbit. So that angular momentum just becomes inherent to the point.
Mm.
And that's how you wind up with that spin, what they call in spin angular momentum. That's how you wind up with it.
Okay. So the DL, so far we are saying the DL will be the same. It will be a
It's
constant.
always it's always the same. It's never different. The
So the distance
DL,
between the distance
the
between,
length between each one of those things you're calling the brain thing,
yeah,
the distance between them is always the same.
yeah,
It's always the
because of this
DL.
electrostatic, some electrostatic or something is keeping them apart, like a surface tension or electrostatic forces will keep them
Well,
separate.
there, there's see that see the DL is part of. Got to remember in there's physical reality is not a fundamental reality. It's continuum reality, physical reality. The actual reality that's from the discontinuum reality, which is the quantized reality. That DL is an immaterial space. That's what it is. It's not a physical space. It's nothing physical at all. It's something that's non-physical.
Yeah, I mean, like electrostatic, that can keep the distance. The sheets different. Like they put a paper on top of each other. There's a distance, right? So now I have paper here, another paper here, and
Well, see,
then
you're looking at it as though there's an electrostatic force, and I'm looking at it from the point of view of realities. There's it's just not part of reality. So
hmm,
there wouldn't have to be a electrostatic force. It's just not part of reality at all.
hmm. So they exist as different brain sheets, like, and then how we have to describe how they move because of the time, the condensed time, the next sheet, the next sheet, the next sheet, they exist at different points, and when you put them together, they see as if it is moving. So they produce like a wave, sine wave, or whatever, cos wave or sine wave. So
Right.
they move like a wave. They seem like a wave, but they are just points, and we are
Well, that's
connecting
why
them
I'm
like.
calling it. That's why I call it a discontinuum sine wave, is because
uh,
there is no continuum.
uh,
That's that's not a fundamental reality. It's always a discontinuum. So the thing that everybody's been calling a a sine wave, which is based upon the wave they always show you, is a continuity wave that has never existed ever. It was always a discontinuity wave. But the DL is so tiny, we never noticed it. There's no such thing as the sine wave as they always explain it to you. That has never existed.
so we are just filling in the gap to show, to see the connection between one and the other, but actually they're existing as different. I mean, there's no thing that actually there's no view. Yeah.
Right. In the reality that exists outside your conscious mind, the the reality we're talking about here, it, right at the moment, is uh, discontinuum reality, which is quantized reality, and it's two separate realities that are together. One of them is continuum reality, which is physical reality, and the other one is no continuum reality, which is non-physical reality. So you have things that you would consider physical, like those brains, separated by things that just a space that just doesn't. There's no expression for it in terms of physical reality. It's a non-physical thing, and that's why the sheets are separated. Is because there's a non-physical thing there. That non-physical thing is the white spaces in that sinusoidal wave that I showed you where all the white
Yeah.
spaces are.
Yeah.
Those white spaces are there because there's no physical thing there. It's an immaterial thing.
Mhm. So that's why what I showed earlier about this stuff, because instead of electrostatics, electrostatic is this, we can see that, this electric field, but it is like time. It's like time, which means that There's no electrostatic. Instead of electrostatic, we can explain in terms of the time tensor. So only time tensor exists between the sheets, but then the scalar, it becomes scalar, the interaction with the gravity gradient becomes scalar, and then you see the physical reality exists. So that makes more sense. So we don't need the electrostatics. I would say instead of this, it's just the TQ, what I call it TQ, exists. The time tensor, which is a time tensor. The time tensor only exists. So there is no reality there. And so they separate. And this time tensor, then the DL is connected with this scalar time, which we are trying to calculate. And this is quantized. This is quantized. The time is quantized. Then this is automatically quantized and definite thing, and so on and so forth. So because of that, we can eventually even, I think it's possible, you have to see, to show that all the DL should be the same. Mathematically, we can, that may be more involved, but eventually, if we describe the complete math, should be able to say all these DL should have same value, definite value, and that value we define in terms of the quantized time that we measure everything. For example, CMBR and the gravitational wave, they are the same for the same source. Of course, we have to ensure that there's the same source. It's very, very important. Like uh, like you said about the Einstein thing, where the time dilation, it uses two different things. They are not the same. Uh, they are not the same point. So the coordinates are changing there. So we cannot compare. It's like comparing apples and oranges. So we cannot do that. In the same way, if you measure the CMBR and it should be the same source, then the time difference will be the quantized time, and that time, this continuum time, what we call a gauge time or quantized time, should be the same because CMBR is a constant thing, and we know that we have measured that, and gravitation wave is a constant thing. So these are constant things that, and the difference between them should be constant, and that constant is the quantized time, which translates to, in terms of space, the DL, that is continuum length, and that should be then quantized or the same value. So that's the conceptual argument, but I think we should be, if we calculate and then we show mathematically, they are all the same, and then they are connected with this quantized time. I think we have, in a sense, proved, it's not complete, almost more than partially we have proved discontinuum. That's one of the proofs for the discontinuum physics. If you can measure that. And then we're connecting to the big thing, which is CMBR and gravitational wave. Uh, I think that's even astrophysically, then it should be correct. Then we can remove a lot of the arguments people may have against that, uh, and then falsifies some of the aspects of the general relativity and quantum mechanics. And then the other aspect, like I said, the pendulum moving and things like that, will be an additional proof that shows that we are and then eventually with that aspect, then you can come back to your table of reality and talk about the realities, why they are the so way, and you can explain again based on that how this reality is what makes us see these things. And like you said about the movies and the cartoons and all that, that also is an additional proof of the it's kind of an illusion in a sense. um, in a sense it's an illusion because we are filling in the gaps just to see that, just to see how the connections between them. But active, like we like you see in the night, we see, for example, stars or the planets or the stars twinkling, and then astrologers, astronomers, I come up with a pattern they think it's like a hunter or a boar or a bull or anything like that. So they connect lines between them, right? But there is no line actually connecting them. We see a separate tingling stars or planets, which does not have much light, but we connect them and see the pattern. And you know, so maybe a very similar situation with these points, quantum mechanical. So
Well,
maybe,
it's it's because the length of the DL is so daggone tiny. That's why you get these interactions.
uh, so they merge together, kind of like if you see two points here. So if you have 2 points, like laser, like 2 points, if they're too close, if they're coming to too close, then we see as 1 point, right? But they are actually two
That's
points.
right. That's right. But they're actually two different points.
Yeah.
Yeah.
So resolution, is there a matter of resolution? So which means if we are calculating significant digit tells you about resolution, we are not able to resolve that yet. But we may never be able to resolve that if the DL is much smaller than bore radius or any length measurements we can make. So which means even with laser techniques.
No, no, I know. That's what I was saying is right at the moment we're just speculating that it's the Planck length when in fact we don't really know that.
Yeah. I think the best way is that quantum time. If we can prove, like what Christian is saying about the time is quantized and attosecond or even smaller than that, and we can measure that. And people got Nobel Prize recently about the attosecond thing. Um, so if they are able to do more, and the time measurement, I think will be more realistic way of proving it. And we say that is quantized for sure, then automatically we can convert that into space and say that 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 the space also is quantized in that sense, which means that with our mathematics and everything, if we prove, calculate the DL, and we say, like I said, like we are mentioning that it may be somewhere greater than LP, somewhere much less than boundary, somewhere in between it could be, and that will make sense. Then these points are too close to each other in terms of measurements, and they appear as one, a continuum thing. So if you have many points, for example, if you have many points, they are separate, but they look like they are continuum, right? So that's what you are saying. But there is a distance between them. So but we cannot resolve this, not resolve. So that's our problem. So, but that was the same case with the laser. You see that initially classical physics said that, but with the laser measurements, we could separate them and see as two different wavelengths. In laser technology, we see that this wave occurs like that, but they occur as one big thing. But the laser said that they do occur as two different things, two different points. So this is a laser, and that's one of the things of quantum mechanics that in a sense that proved about quantum mechanics, but there's other problem. Maybe there's a discontinuum aspect, you know, because they're describing some superposition, wave function collapse, things like that, but it may be just a illusion thing, like you're saying that they're not the same. They're not the same.
Okay. Yeah. Right.
So that
I'm going to have to take off.
okay.
I have some other things I got to get done today.
Okay.
So I'm going to have to take off.
Okay. Thanks, Emery, because I
Okay.
think you clarified a lot of things, and then we had good discussion. Then what we are, and I'll try to see whether I can code it. If I cannot, then I have to wait till next week that Christopher comes back to complete. But I will keep working on the coding, debugging, programming that thing, so get our stuff. And if we can get that, lo and behold, you're lucky. Otherwise, I have to wait till Christopher to come, because I don't want to, you know, create some code which is not, rigorous and things like that. I don't think it's worthwhile to putting that in our paper. It should be rigorous that anybody puts that code, they should be able to generate that. It should be reproducible.
Yes,
So
yes,
we'll be very,
yeah,
very, very strong. You become experts in that. So that's what I want, because we have so many papers. Now our next step is to become expert in that people can we can show in a presentation or thing. Yeah, you do that, you get exactly that. So it's exactly that's how we are going to proceed. So mathematical formulas are very rigorous, very thorough, and also without any you know question. It's fundamental. So I want to make it like that. I don't want to publish things that is kind of half hazy or something like that. I think your papers are very clear. Your papers are also clear. My papers are, mathematically they are clear, and I take my time, to rethink. So if you're not sure, I wouldn't probably publish it. So like that, because the other one part is clear. The case one, I think, is clear. The case 2 and 3 are, we need that code. And I wouldn't be surprised, because as we go along, the complexity will increase. It will be harder and harder to prove. The mathematics require more and more, deeper thinking and work. So, but we'll do that. So ensure that every step we are doing it correctly. That'd be great. So thank you very much, Emery, input for coming, and then hopefully we'll continue. If you are able to come, you won't be able to present your grade cost next week, right? Because we have.
okay.
This is what we have put up. Let me see. This is what Christopher has put up for last week. Oh, I have to get out of it. Let me see. Uh, it's there. I don't think no, I cannot show that yet. It is not there. Let's see. Um, yeah, I have to get out of it. Show. So actually, I cannot show. I cannot. I can. So the grade cost, he has put it next week. Your presentation, but like you said, are you able to present your Audi grade, the grade request next week?
No, I haven't even looked at it.
Okay, okay. So I'll
I
tell
haven't even looked at it. I've
Christopher.
been so
Yeah.
so busy working on paper 12.
Okay. Yeah, that's what I thought. I told Christopher that, yeah, we are working on uh, we are working on this paper 12, which is taking more time. And so next week again we'll continue, and then if Christopher comes back, if I didn't finish the coding, we'll try that. Uh, and then if you can do that, otherwise you may have to just put case one, case two, and case three. You can say, we are working on it, and then we'll eventually prove that, and also calculate our DL. If you want to put that, you can do that. Uh, so if you have some solid, real good thing, I will let you know. But if I don't have a solid thing, I don't think I will. It won't. I wouldn't be comfortable, to publish that yet. But if it is solid thing like the case one, case two, if you are lucky, then it shows up without Christopher's help. Otherwise, we need a Christopher's help to complete that. So then we'll eventually add on. Thank you. So have a nice weekend. Thank you all. We'll continue next week. Okay, so I think yeah, we need to switch it off. But anyway, all of you, goodbye. Is the last uh, aspect that you want to talk about, and everybody also has signed out. So we'll sign out for now, and we'll continue resume next week. And we have to have more advancement on our thing. I think we have a good discussion, but we will have to continue to make it more rigorous. Thank you. Thank you all. See you all next week.